Hi folks, welcome to the second half of the calculus recap for the IB AASL Mathematics course. In this video, we'll be looking at area between curves, at kinematics, and at a few other applications. There's a link to the first part of the video in the video description below. This is not an exhaustive list of all the things in calculus, it's just a review that I made for my students in PEI Canada. You can find timestamps and downloadable notes in the video description, and you can make use of YouTube's many accessibility options. One of the best ways to get a lot out of the video is to pause it and try the question yourself. Please be aware that there are often many different ways to do a question, so if you have a different method than me, that's great. Keep doing what you're doing. Alright, with that out of the way, let's dive in. The first thing that we'll look at is area between curves. And the way I like to think about it is that if you want the area, you just take the left bound to the right bound of the top function minus the bottom function. So these are top function minus bottom function. So in this question over here, we can see that we've got a parabola, and we're looking for this kind of area right here that's enclosed by the x-axis and that parabola. Now, in my mind, the function that's on top is this one right here. The function that's on bottom is the x-axis, which is y equals 0. Okay? Now, it might be overkill to think about having two functions here, but there are going to be situations that are more complicated, so having one technique that's going to work all the time may end up being beneficial. That said, anytime you want to take a shortcut, feel free. What's important here is that we find out where these x-intercepts are. So to find an x-intercept, we just set y equal to 0. So in my function, I'll say 0 equals negative x squared plus 4. That means x squared equals 4, where x is plus or minus 2. Okay, so this x-intercept's at negative 2. This is at positive 2. And I can use this technique of area is the left bound to the right bound of the top function, which was negative x squared plus 4, minus the bottom function, which was y equals 0. And again, maybe that's overkill. And then we have dx. And so maybe I can simplify this, and perhaps this is where a lot of people would just want to start this question. Now, if this is a GDC question, just dump it in your GDC. If it's not, then we have to go through this analytically. So that means anti-differentiating. We'll get negative x cubed plus 4x. And our boundaries are negative 2 and 2. And then we'll sub in. Since we did a bunch of definite integrals in the last video, I'll just have the steps appear. So here's big F of 2 minus big F of negative 2. And I'll just work those out. I'll need a common denominator. And then I'll just put it all together for a final answer of 32 over 3. And it would be appropriate here to say units squared because we are talking about area. So there we go. We're done. If we wanted to do this on the GDC, then I'll do the definite integral. I'll go alpha, window, and 4, or you can find it under math. And I'm just going to type in this integral right here, negative 2 to 2 on negative x squared plus 4. I hit enter, gives me 10.66666, which is 10 2/3, or 32 over 3. If you want to, you can use the fraction button to have it convert the answer into a fraction. Or on a paper 2, we can just leave it as 10.7. Now let's play the IB's favorite game, which is to put the variable somewhere a little unexpected. So in this question, they're telling us that the area from 1 to m between this function and the x-axis is 3 units squared. Now, I think a lot of people are just going to go and take the integral of y and say that that's equal to negative 3. And that's great because it's area below. I'm going to use this same area technique every time, though. Anytime I want area, it's the integral from left to right of the top function minus the bottom function. So the area here is 3. The left boundary is 1. The right boundary is m. The top function in this case is y equals 0. Okay, so I would have 0 minus the bottom function. And the bottom function is the one that's given. It's negative 1 over root x. I apologize if my voice is given out here. Apparently my body is rebelling against these videos. So we have 1 over root x dx. Okay. Or better yet, let's call that 1 over root x. Let's just call it x to the power of negative 1/2. And then we can just integrate as per usual. So 3 is going to equal, what's the antiderivative of x to the negative 1/2? The power goes up by 1, and the flip of the new power goes in front, from 1 to m. And now we'll sub in, so we have 2m to the power of 1/2, or square root of m if you prefer, minus 2, 1 to the power of 1/2, or 3 equals 2m to the power of 1/2, minus 2. We can move that 2 over, so we get 5 equals 2m to the 1/2, or 5 over 2 equals m to the 1/2, or root m. And if we want m on its own, then we're going to need to square both sides. So we'll get m is 25 over 4. So here's a question where the variable is somewhere a little bit different. We could check that this answer works on our GDC, and I'll leave that to you if you want to do it. But this is going to be the correct value for m. All right, that brings us to the area between curves. So I've got this polynomial g of x, or this cubic g of x, and this line f of x. And I'm wondering, what is this shaded area? So I can see that g of x is on top. The area is going to be the integral of g of x minus f of x dx. I can also tell that the left boundary is 0. What I need to find is this right boundary. And maybe I need a little more space. If I want that point of intersection, I can just put the two functions into my calculator. So I'm going to put those functions in. I'm going to choose window settings that are similar to the ones that I see in front of me. I'm going to graph, and I'm looking for that point of intersection. So I go second, calc, intersect is 5. I have to choose a left bound. This may be a hair different on your calculator than my emulator. And a right bound, and on my calculator I also have to guess. But it tells me right there in purple that the point of intersection is 2.58579. That's the y, or the x value rather. There's the same y value because it's the curve y equals x. I don't really care about the y value, but that tells me my right-hand boundary. And I should probably keep a bunch of extra sig figs here because it's not the end of the question. So I write that in. I've got the integral from 0 to 2.58579 of g of x minus f of x. Let's do this on the calculator. Definite integral, I can find it under alpha window or under math. I'm going from 0 to 2.58579. And here, instead of writing the functions out again, I know that I put my g of x in y2, so I press alpha trace. I can just choose y2. Minus, again, alpha trace, and I'll choose y1. You can find these in other places too. Work it out to 3 sig figs, we get 11.9 units squared. Now we're going to repeat the same process for the same functions, but there's going to be 2 different areas that we're looking for, and we need to find the sum of them. So I already know that this is happening at 2.58579, whatever. Don't care about the y value. And I also need to figure out what the second intersection is, so that's no big deal. I graph, I go second, calc, intersect, and I find that other point of intersection. Left bound, right bound, in purple it tells me 5.41421. And the y value will be the same, but I don't really care about the y value. Here's the rub in this case. The roles of the function change. So over the first little section from 0 to 2.58579, g of x is on top. For the second half, f of x is on top. So I would have to do these separately, 58579 to 5.41421, but this time with f of x on top. F of x minus g of x dx. Okay. And if I worked those out, I would get the correct area. Now there's also a trick that you can do with your GDC, though, that might save you some time. So this GDC hack is that you just take the integral from the far left boundary to the far right boundary, and you don't even worry about which function's on top. You just take the absolute value of the difference, which is going to keep it all positive, and this will work out for us every time. We don't have to worry about multiple points of intersection in between, or which function's on top. So let's work it through on the GDC. I'm going to quit here, second mode. I'm going to go alpha window to choose the definite integral. I'll go from 0 to 5.41421. And then when I get down here, I'm going to choose absolute value. That's under math, and I press over to the right for ABS. And I can say y1, so this is under alpha trace, y1 minus y2. Now, on your calculator, it may chug a little bit to find this value because it's computationally kind of difficult for these calculators. It's not going to on the emulator here. It's just going to give us a value of 27.0 units squared, which is faster than doing it the way that's in black up top. But you should probably be aware of both techniques, that if you have a difference in which one's on top and it's analytic, you probably need to split it into two separate integrals. If you have access to your GDC, well, we can avoid all these shenanigans by using absolute values. While we're at it, we might as well tackle asymptotes. So vertical asymptotes come from what makes the bottom 0 and doesn't divide out nicely. So in this case, 1 would, there's our vertical asymptote. You don't write vertical asymptote equals, you write x equals, because x equals a constant is a vertical line. The other thing we need to do if we want the horizontal asymptote is imagine what happens to y as x gets large. Now, really, that is a limit as x goes to infinity, and maybe you need to consider it both in the positive and negative directions. But for the case that we've got right here, we can just imagine what happens if you put in a huge x value. And if you're having a hard time imagining that, then maybe what we want to do is think about this. What if we had put in 1,000,000 for x? Okay, 1,000,000 is not unbelievably large, but it's very big. If I had 2 plus 3 over a little less than 1,000,000, I mean, that's going to be 2 plus a very tiny bit. It's going to be basically 2. Okay? That number that you're heading towards, that is your horizontal asymptote. If you want to do it more formally using a limit, feel free. But that's what we're asking. What happens to y as x gets very large? So there are our two asymptotes. Let's move on to another classic question type where we're given a derivative and asked to find the original function. So we're told that the second derivative is 2x minus 2, and there's a minimum on f at 3, negative 7. That tells us a couple of things. That tells us that f of 3 is negative 7. But more sneakily, it also tells us the slope at 3. If there's a smooth minimum at 3, that means the slope at 3 is 0. Okay? And both of those facts are going to help us out quite a bit. If we know the second derivative and we want to find the first derivative, that means bumping it up a level, and that is the job of integration. So if you want to be really clear about it, you could say the first derivative is the indefinite integral of the second derivative. In other words, we're looking at the integral of 2x minus 2 dx. And that's not that bad to integrate. We're going to get x squared minus 2x, and careful here, you need a plus c. Now we're going to hunt down the value of c. So now we can sub the fact that f prime of 3, or the slope at 3, is 0. So if I put 3 in for x, I should get a slope of 0. Okay, in other words, 0 equals 9 minus 6 plus c, or c equals negative 3, or the first derivative, with its c sort of sussed out because we have this extra information, is going to be x squared minus 2x minus 3. Now we're going to bump it up another level. If we want to find the original function, well, that comes from integrating the derivative. So f of x will be the integral of x squared minus 2x minus 3 dx. And what will we get? We'll get 1/3 x cubed minus x squared minus 3x plus another constant of integration. Now, I'm just going to call it d. You can use whatever letter you want. Some people use c sub 1, c sub 2. Now, in order to find the value of d, I can sub f of 3 gives us negative 7. In other words, if I put 3 in for x, I should get negative 7 for y. Let's work this out. That'll be 27 over 3, so that's 9 minus 9 plus d equals negative 7. Work it all out, and we're going to get d equals 2. And then we have to actually express the final function. So the original function that we're talking about is 1/3 x cubed minus x squared minus 3x plus 2. Now, if you want, you can differentiate twice. Make sure that it gives you that same second derivative you were expecting. But I think it's going to be all good here. That brings us to another common application of derivatives, which is to find the equations of normals and tangents. So a normal is a line that is perpendicular to the tangent. Let's assume that we're doing this question on paper 1. We want the equation of any line. Well, to find the equation of some line, we need to know a point, and we need to know a slope or gradient. Okay, so I know that the x value is 1. The y value that's going to come from this is going to be y equals 1 minus 3 times e to the 1, or in other words, negative 2e. Now, if you had your GDC, you could find that by using the value function on the graph. For the slope, well, that's going to be the job of the derivative. And I'm going to need to use a product rule. So I need to take the derivative of the first part, which is 1, times the second, plus the first part, x minus 3, times the derivative of the second part. Well, the derivative of e to the x is still e to the x. So that's e to the x plus x e to the x minus 3e to the x. Or y prime is going to be x e to the x minus 2e to the x. That's the slope anywhere. We want the slope at x equals 1. So that will give us 1 times e to the 1 minus 2e to the 1. Or just negative e for all that work. The slope we're looking for, though, is not the tangent slope. So this would be the slope of the tangent. We want the slope of the normal. So that is going to be the negative reciprocal. And since it was negative to begin with, that'll turn it positive. So for all that work, we found the slope of the tangent, and then we took the negative flip of it, or changed the sign and flipped it, to find the slope of the normal. Okay? And that'll always be the property between tangent and normal. They're reciprocals with the sign changed. Now we are able to use the point slope formula to find the equation of this line. Okay? So y minus negative 2e equals m, which is 1 over e, x minus 1. So this would be our x1 and our y1 over here. Or y plus 2e equals 1 over e times x, or x over e, minus 1 over e. And if we move stuff around, we're going to have 1 over e x minus 1 over e minus 2e. There it is in perfect form. If you had done this with your GDC, I think you probably would have got this as your equation. 3.368 minus 5.80. That's okay as well. Either one's lovely. And now it says find the coordinates where the normal cuts f of x again. So we're going to assume a GDC can be used. There's the function. Where the blue dot is roughly at x equals 1. So it's going to cut there. Let's put in the equation of our normal line. And I'll hit graph. And it really does touch at x equals 1. What we're wondering about is what's that other point of intersection, the one further to the right. So I'll go second, trace, I choose intersect, and I need to give it left and right boundaries. So a little to the left and a little to the right. And you may have to guess on your calculator. Here it tells me 2.66 for the x and negative 4.82 for the y. There's the curve. This is the point we're talking about, 2.66, negative 4.82. So we did some analytic stuff, and then we did some GDC stuff. Okay, that brings us to one of our biggie applications, kinematics, or the mathematics of motion. So at the top of the heap here is position or displacement. The derivative of displacement is velocity. So velocity equals s prime of t. The derivative of velocity is acceleration. So acceleration is v prime, but it's also the second derivative of position. If you want to go down this chain, well, then you're differentiating. If you want to move your way back up, well, then you're integrating. So the velocity function of a particle is given by this weird function here. When t equals 3, the particle's 5 meters right of the origin. Find the position relative to the origin when t equals 4. We're going to do this two different ways, but we'll just do it sort of the basic way for now, and we'll come back to it. Option 1, if you want the position function, you should integrate the velocity function. Okay, that's a big idea. So if we want to integrate this, then we're going to need to work it through term by term. 3t squared is t cubed, e to the 2t, that's going to be 1/2 because of that 2t, e to the 2t, and 1 over t comes from a ln t. We're ln absolute value of t, but our time is all positive here, so no big deal. And plus c, that's important. Now, I would double check this. I'd check my integration every time. It'll give me 3t squared, it'll give me -1/2 e to the 2t times 2, and it'll give me original on the bottom, derivative on the top. Great, it'll give me everything that I thought I should start with. That gets me back to the velocity function. Okay. Even explaining it through took like 20 seconds, so it was worth it. Now we're going to sub in something. We know that s of 3 is 5. When we say right of the origin, we mean positive position. So if I put in 3 for t, okay, there's 3 in for t, I should get 5 for my position. And if you work that through, you'll get c is roughly 178.6. I'm keeping at least one extra sig fig here because I'm a little nervous. It's not the end of the question. And so that tells me now that the position function is t cubed minus 1/2 e to the 2t plus ln absolute value of t plus this c value that we found, which is 178.6. Okay, that is the position at any time. If we put in 4, well, we can see what happens. Now this is really tedious, so I'd be inclined to put in the function in my calculator. So I've actually put in the velocity function for y1. I'm going to turn that off because that's not what I want to look at. I want to look at the position function. And if I want s of 4, I can hit graph. And on your calculator, you can probably go second trace and type in value. It doesn't work great on my emulator. But whether you do it just by plugging in the values or whether you actually use the graph, we should get s of 4 is -1246, or to 3 sig figs, -1250 meters. That's the position. The next thing we're asked for is the acceleration when time is 4. So let me just write that. Acceleration when time equals 4. And you might be inclined to take the velocity function and differentiate it down and then sub in, which is absolutely fine. But it's important to notice here that that just means the derivative of velocity when time is 4. So we're looking for v prime at 4. And we can probably use our calculator to find this easily. I put in the velocity function in y1. If I hit either alpha window or math, I can get to n deriv, okay, numerical derivative. And I can ask it to find the derivative of alpha trace, so of y1, when x is 4. And it will just work that out for me. It's -59.40 to 3 sig figs meters per second per second. We could also be asked, is the particle speeding up or slowing down at t equals 4? And that has to do with the relationship between velocity and acceleration. So we already know that a of 4 is -59.40 meters per second per second. What is v of 4? Well, if you just sub it into the original, either using some of your graphical features or however you want to do it or by hand, we'll get that it's about 2930 meters per second. And since they're both negative, or they both have the same sign, that means we're speeding up. As a rule, we would say If velocity and acceleration have the same sign, we're speeding up. If they have different signs, then they're kind of working against each other, and we're slowing down. There are other ways that you could do these two questions, but I think these are ways that require the least amount of extra work. This all leads us to more kinematic goodies. Net displacement, or the change in position, the net change in position, is given by the integral of velocity. The total distance traveled is given by the integral of speed. So the absolute value, or the magnitude of velocity, is speed. Okay. So let the velocity of some object in meters be given by this. And if we want the net displacement from 0 to 5, well, that would just be a regular old integral. I can do this on my GDC. I'm going to take the time to put in the function x squared sine x, okay, and also to check that I am in radian mode. And I am. So now I can just do this integral. Alpha window, fn integral, or you can find it under math, and I'll just tell it use that y3 function. So that was under alpha trace. Bam. It tells me negative 18.1 meters. Okay. Now, what does that mean? Here's the simple explanation. It means it ended up 18.1 meters left of where it started, or in the negative direction of where it started. If we want the total distance traveled, well, that's going to be the integral of the absolute value of velocity. Okay. And if velocity is positive, then, and it's always positive, then it really doesn't matter if we have those absolute value signs. So we'll go alpha window. Again, I'll choose definite integral 0 to 5. I'm going to use this time the absolute value, so that's under math, and go over to number, and you choose the absolute value signs. And I'll go alpha trace to choose y3, because that's where I put my velocity function, and I'll get 29.9 meters. I'll definitely get a positive one when I use these absolute value signs. Now, what does this mean? It means it traveled 29.9 meters. Now, why are these two things different? Well, because there are turning points happening, so it changes direction. But there's the cliff notes on net displacement versus total distance traveled. To generalize a little from this, the fact that the definite integral of velocity is net displacement tells us that the definite integral of a rate in general is the accumulated net change. So the change is going to be the integral from t1 to t2 of some rate. The population of a town is currently 5,000 and is growing at a rate of this function right here, where t is time in years. By how much will the population increase over the next 12 years from today? So by how much will it change? Well, the change will be the integral from 0 to 12 of that rate function. And I'm going to put that rate function in my calculator. To be honest, by the time I'm done of a paper 2, I usually have all 10 of my functions filled in so that I can come back and check my answers later, and I don't have to type things back in. So there we go. I'm going to quit, and I'm just going to find the integral of that. So alpha window, definite integral from 0 to 12 of y4. That's where I put that one in. And it tells me 4640. Okay? That's how much the population increased by. What would the population be 12 years from today? Well, that would just be the initial population plus the change. And the initial population was 5,000. The change is 4640. There are other ways that you could do this, but I would say that this is probably the slickest. So, an integral gives you net accumulated change. The integral of velocity gives you the net change in position, or the net displacement. Let's revisit our kinematics question for 1 second here. This first one said find the position when t equals 4 seconds. The slickest way you can do this is to take the position at 3 seconds and add on the change in position, the net accumulated change in position, or the net displacement. So we know s at 3 is 5, And the integral of velocity from 3 to 4, well, we can do that in our GDC. I still have that velocity function in for y1. So I'm going to go alpha, window, definite integral, just from 3 to 4 of y1. And it's going to give me negative 1251-ish. Okay, and put that together, I'll get negative 1246, which to 3 sig figs is negative 1250 meters. And really, I didn't even need to see these two steps. I could have gone straight from here to here. That is less work than we did the first time we did this question, right? But if you don't notice that, well, then you've got other options. So this would be option 2 here. This brings us to the very last topic that I'm going to deal with in these calculus videos, which is optimization. These are really just questions where you're asked for a max or a min. So they could be really easy questions, or they could be quite complicated. And we might be sometimes looking to optimize something like time. Sometimes it might be cost. Sometimes it might be area. We have to read carefully. So optimization is the mathematics of finding a max or min quantity. If possible, draw a clear diagram if you don't already have one. Construct an equation with the variable that you want to optimize, whether that's cost, volume, area, whatever. Now, when you make your equation for the thing you want to optimize, you may have way too many variables in it to start with. And then you start to see if there are things in the question that can help you whittle it down so that you just have the thing you want to optimize and maybe one other variable, x. But don't get discouraged if on your way there you're at an equation that looks kind of messy, or even one that looks kind of juvenile. You start with a grip, and then you work on getting a better grip. You're going to find your min or max using either the GDC, the first derivative, and a sign table, or maybe you'll use the second derivative test to make sure it's a max or a min. Often in the optimization questions, they won't ask you to justify that it's a max or min. So if you find the place where the slope is 0, you've probably found what you're looking for. Angie has decided to create a rectangular enclosure, as all people in math textbooks do. They love making fences. She wants a total area of 30 square meters. Okay, so let's draw this here. She's got a rectangular enclosure, and she's got to be 30 square meters. Okay, and she knows that the cost for 3 of the sides is $4 per meter, and the material required for the fancy front is $9 per meter. Write an equation for the cost of the materials and find the dimensions that minimize this cost. Yeesh. Okay, let me think about this. I've got some sides here. That's an X, that's an X, that's a Y, that's a Y. Let's call this the front here. Okay. So cost is going to be, both of those Y's are going to be $4 per meter. So cost will be 4 times Y plus another 4 times Y. The back over here, that's only $4 per meter. And then the front is $9 per meter. So the cost is 8Y plus 13X. That's actually an okay equation for us to start with. I do kind of hate the fact that it has a Y in it, but now I'm going to see if I can improve my equation. So I have a grip. I'm going to work on getting a better grip. And here's what I know. I know that the area of a rectangle is length times width. And the area here is 30, and the dimensions are x by y. In other words, y is just 30 over x. I can use that fact to replace the y's over here to make a substitution with 30 over x. Okay, so I get 8 times 30 over x plus 13x. And that would allow me to create an equation that graphs cost against x, where x is the width of the front. If this is a paper 2 question, that's all you need. If it were me, I would not even bother multiplying the 8 by the 30 for a paper 2. I'd just go 8 times 30 over x plus 13x. I'd take a second and think about reasonable window settings. Like there's going to be no negative x values. So x might go, 10 is pretty wide for this, so that sounds okay. Now, the y values, it's not going to be a negative cost, so cost is on the y-axis. Are we going to be able to make a fence for $10? Probably not. probably in the neighborhood of 1,000, but maybe that's overkill. We'll find out. We'll just graph. If it's not a great window setting that we've chosen, then we'll go ahead and find a different window setting or refine it. So what I'm going to do now is I'm going to go second, trace, and look for the minimum. And I go to the left of the min, and I go to the right of the min, and you may end up having to guess on your calculator. For mine, it will find it for me at 4.30, okay, and 114 for the cost. So I guess it wasn't thousands of dollars. That gives me X and cost. Let's make sure we actually answer the question. Write an equation for the cost of the materials and find the dimensions. Oh my. So we've got a width of 4.3 meters, and we've got a depth of y, and y is just 30 over x. So that would be 30 over 4.30 meters. That would give us 6.98 meters. If this is paper 2, we are done. Now, if this is paper 1, we're going to have to find that min value analytically. So I might rewrite this equation, the cost equation, like this. 240 x to the minus 1 plus 13x. Okay. And the reason I'm going to do that is because I'm going to differentiate. So this will become negative 240 x to the minus 2 plus 13. And I'm going to hunt a minimum. And that means that you set the derivative to be 0. You want the slope to be 0 if you want a minimum. So that would be negative 240 over x squared plus 13 equals 0. You could times everything by x squared, so that'll give you negative 240 plus 13x squared is 0. Or 240 equals 13x squared. And we could keep going here. X squared is 240 over 13. Or x, normally we'd have a plus or minus, but there's no such thing as a negative length. X is root 240 over 13, which it's not going to surprise you to find out is approximately 4.30. Okay. And then if we wanted the y value, well, it would once again come from this 30 divided by root 240 over root 13. So if we want to get that in a nicer form, if we're dividing fractions, we just flip and multiply. And so I can get root 13 over root 240. Because the IB is not going to want us to have nested fractions or stacked fractions as our final answer. Now, honestly, I don't think they're going to give you numbers that are this brand of unpleasant. Who knows? I think this is a better paper 2 question than a paper 1 question. But if you did have to hunt down those values, there they would be, and they would be equivalent to the decimal ones that we found over here. So in decimals or paper 2 land like this, in the smug satisfaction of exact values, it would be this. All right, that brings us to the end of the calculus recap. I hope this has been helpful. Good luck with the material, folks, and take care.